Welcome to the Restful Stories channel. In the silent, boundless expanse of the cosmos, countless worlds drift through the eternal night, each with a unique story waiting to be told. We are drawn to these stories, to the epic narratives of planetary formation, cosmic violence, and the quiet, patient evolution of distant spheres. If you enjoy exploring these cosmic narratives, do consider subscribing to the channel so you are notified of our future stories. Among the celestial bodies of our own solar system, one in particular holds a special dominion. It is a world of such immense scale and power that its very presence has dictated the history and the architecture of its entire planetary family. This is not merely a planet. It is a giant, a king, a gravitational anchor that has guarded the inner worlds for billions of years while shaping their destinies with an invisible, inexorable hand. Its face is a turbulent canvas of storms larger than our own Earth. Its interior, a realm of exotic matter, forged under pressures we can barely comprehend. And its retinue of moons forms a miniature solar system of incredible diversity and scientific promise. We speak, of course, of the planet Jupiter. Tonight, we journey to this magnificent world to explore the story of its ancient past, its dynamic present, and the profound influence it has had on our own place in the universe. Let us venture into the heart of this gas giant and uncover the secrets of the true monarch of our solar system. In the grand cosmic theater of our solar system, one celestial body reigns supreme in both stature and influence, a true monarch among worlds. This is the planet Jupiter, an entity of such colossal proportions that it fundamentally dictates the gravitational rhythm of its celestial neighbors. To call it the largest planet in our solar system is an understatement. It is a category unto itself. Its sheer scale is difficult to comprehend, a challenge to the very limits of human imagination. When we speak of its mass, we find that it is not merely larger than its planetary brethren, but overwhelmingly so. If one were to gather every other planet, from the scorched plains of Mercury to the frozen frontiers of Neptune, and place them on a theoretical cosmic scale, Jupiter would still outweigh them all, combined by a factor of 2.5. This single world accounts for the vast majority of the planetary mass orbiting our sun, a gravitational anchor that has shaped the very architecture of our system for billions of years. Its relationship with our own world is one of stark contrast. Jupiter's mass is a staggering 318 times that of Earth, a figure that paints a vivid picture of a giant and a pebble. This immense gravitational authority, however, conceals a peculiar paradox, a counterintuitive truth governed by the exotic physics that reigns in its deep interior. Should this giant continue to accumulate mass, it would not necessarily grow larger. Instead, beyond a certain threshold, the planet would begin to shrink. The relentless inward pull of its own gravity would intensify, compressing the hydrogen and helium in its core so fiercely that the entire globe would become denser, its volume contracting even as its mass increased. This is the strange reality of worlds that exist on the precipice between planet and star, where the rules of matter behave in unfamiliar ways. The volume it does possess is simply cavernous. If one could use our home planet as a unit of measure, more than 1,300 Earths could be comfortably nestled within its atmospheric shell, a testament to its almost unfathomable capacity. This immense girth is measured at a staggering 142,984 kilometers, a distance that translates to nearly 89,000 miles across. To place this in a more familiar context, one could line up 11 Earths side by side and still not quite span the full breadth of this gas giant. Yet for all its size, the planet is not a perfect sphere. Its form is what astronomers refer to as an oblate spheroid, a shape that betrays the incredible forces at play upon it. This means it bulges noticeably at its equator while being discernibly flattened at its poles. This distinctive form is not an accident of its creation, but a direct and dramatic consequence of the planet's astonishing rotational velocity. The difference is not trivial. Jupiter's equatorial circumference is a full 7% larger than its polar circumference, a visible distortion etched upon its very being by its relentless spin. This spin is faster than that of any other world in our solar system. Despite its gargantuan size, Jupiter completes a full rotation on its axis in just under 10 hours, specifically about 9.9 hours. This incredible speed creates a centrifugal force that flings the equatorial regions outward, shaping the planet into its characteristic squashed sphere. The experience of a day on Jupiter is a dizzying, fleeting affair, a rapid cycle of light and shadow sweeping across its turbulent cloud tops. In stark contrast to its fleeting day, its journey around the sun is a long and stately procession. A single Jovian year, the time it takes to complete one full orbit, is equivalent to 11.86 Earth years. For nearly 12 of our years, Jupiter traces its vast, slow path through the zodiac, a distant, patient wanderer whose internal clock ticks to a rhythm profoundly different from our own. This profound difference in its temporal rhythm extends to the very climate of the planet, or rather, its remarkable lack thereof. While Earth experiences a rich tapestry of seasons, a direct result of its 23.5-degree axial tilt, Jupiter remains in a state of perpetual, planet-wide meteorological stasis. Its equator is tilted by a mere 3 degrees relative to its orbital plane, an almost perfectly upright posture as it journeys through space. This minimal inclination means that the sun's rays strike the planet with near uniform intensity across its vast face throughout its long year. There is no significant spring summer, autumn, or winter on Jupiter, only the enduring, unchanging character of its atmosphere, a world locked in a climatic state that shifts only over geological timescales. But this journey it takes is not a solitary one. Jupiter is the gravitational shepherd of a vast and ancient retinue, sharing its orbital path with an astonishing collection of celestial wanderers. We now know of more than 10,000 of these companions, cosmic rubble left over from the formation of the solar system, which are known as the Trojan asteroids. These objects are not scattered randomly, but are corralled by the planet's immense gravity into two stable regions, known as Lagrange points. Imagine two invisible gravitational safe harbors, one positioned 60 degrees ahead of Jupiter in its orbit, and the other 60 degrees behind. In these zones, the combined gravitational pull of the Sun and Jupiter creates a region of stability, trapping any objects that drift into them. And so, two great clouds of asteroids, each a sprawling city of rock and ice, silently precede and follow the giant planet, a permanent celestial entourage on its stately procession around the Sun. This gravitational dominance is a direct consequence of what Jupiter is fundamentally made of. It is the archetype of the gas giant, a world constructed not from rock and metal, but primarily from the two most abundant elements in the universe, hydrogen and helium. In this, its composition mirrors that of a star, and indeed, Jupiter is often described as a failed star. It possesses the same raw ingredients as our Sun, but lacks the sheer mass required to ignite nuclear fusion in its core. Had it grown about 70 times more massive, the pressure and temperature at its center would have reached the critical point to begin burning hydrogen, and our solar system would have been a binary star system, a profoundly different place. Lacking this internal fire, Jupiter remains a planet, but one whose nature is defined by its gaseous, star-like makeup. This composition gives rise to the largest planetary atmosphere in the solar system, a swirling, dynamic ocean of gas that is as deep as it is wide. When we gaze upon Jupiter through a telescope, we are not seeing a solid surface, but the very top of this colossal atmospheric shell. Its face is a mesmerizing canvas of color and motion, striated with distinct, parallel bands that circle the entire planet. These are not static features, but are in a constant state of flux, their appearance changing on a daily basis. The lighter, cream-colored bands are known as zones, while the darker, rust-colored ones are called belts. These are regions of rising and falling gas, respectively, and they mark the boundaries of immense atmospheric currents. The zones are areas of higher pressure where gas is upwelling from deeper within the planet, cooling and forming bright clouds of ammonia ice. The belts, conversely, are regions of lower pressure where cooler gas is sinking, revealing the darker, more colorful cloud layers beneath. The creation of these bands is driven by incredibly powerful east-west winds, formidable jet streams that flow in opposite directions. The sheer velocity of these atmospheric rivers is staggering, with wind speeds reaching up to 539 kilometers per hour, which is about 335 miles per hour. These are winds far more powerful than any hurricane ever recorded on Earth, and they are a permanent feature of the Jovian climate. The friction and turbulence generated where these opposing jet streams meet are what give rise to the swirls, eddies, and colossal storms that pepper the planet's surface. Yet for all this grandeur, the visible clouds we see are but a gossamer thin veil. This entire, visually spectacular cloud deck is thought to be only about 50 kilometers, or roughly 30 miles, thick. The vibrant colors that paint these clouds are a product of their chemistry, with the ammonia ice crystals at the highest altitudes forming the white zones. Deeper down, it is believed that the atmosphere is structured into at least 3 distinct cloud layers, each with a different chemical composition, including layers of ammonium hydrosulfide and water ice clouds, which contribute to the rich palette of reds, browns, and yellows. Beneath this relatively thin veneer of clouds, the concept of a surface dissolves entirely. There is no solid ground to be found on Jupiter, no bedrock or planetary crust upon which one could stand. Instead, as one descends deeper into the planet, the atmosphere simply becomes progressively denser and hotter. The relentless increase in pressure transforms the gas into a state unlike anything on Earth. It is a world without a shore, an endless continuum where the distinction between gas and liquid blurs and eventually disappears. A truly bottomless ocean of swirling, super-compressed fluids. As we plunge deeper into this seemingly bottomless world, we encounter a realm where the laws of physics are pushed to their absolute limits, a place of truly alien conditions. Far below the churning cloud tops, the crushing weight of the overlying atmosphere exerts a pressure that is millions of times greater than the sea level pressure on Earth. Under this immense compression, the abundant hydrogen gas undergoes a remarkable transformation. It transitions from its familiar gaseous state into a liquid, creating the single largest ocean in the entire solar system. This is not an ocean of water, but an exotic sea of liquid molecular hydrogen, a vast and turbulent body of fluid extending tens of thousands of kilometers deep. The sheer scale of this internal ocean is difficult to overstate. It is a feature that fundamentally defines the planet's interior structure and dynamics. But the journey into Jupiter's heart reveals an even more extraordinary metamorphosis of matter. As we descend further still, the pressure continues to build to unimaginable levels, eventually exceeding the strength of the bonds that hold the hydrogen molecules together. The electrons are squeezed away from their protons, and the hydrogen becomes a freely flowing sea of charged particles. In this state, it behaves not like a familiar liquid or gas, but like a metal. This is liquid metallic hydrogen, a substance that can be created only under the most extreme conditions of pressure and temperature. This metallic ocean, which is thought to comprise the bulk of Jupiter's interior, is a powerful electrical conductor. The planet's rapid rotation, completing a full spin in under 10 hours, churns this conductive fluid, creating a colossal dynamo effect. It is this process that generates Jupiter's immensely powerful magnetic field, the most formidable in the solar system. The very heart of the planet, however, remains a profound mystery. For decades, planetary scientists theorized that at its center lay a small, dense core of rock and ice, a solid seed around which the rest of the planet accreted. However, recent data from NASA's Juno spacecraft, which has been orbiting Jupiter and probing its interior with sensitive gravity instruments, has painted a much more complex and surprising picture. The data suggests that the core is not a neat, solid ball. Instead, it appears to be a fuzzy or dilute region, a vast, slushy mixture of heavier elements like rock and ice that are partially dissolved and mixed into the metallic hydrogen above. It seems that the traditional, clearly defined layers of planetary structure do not apply to Jupiter. Its core is a diffuse transitional zone, a discovery that is forcing scientists to rethink their models of how giant planets form and evolve. This strange interior is also the source of another of Jupiter's defining characteristics: its powerful internal heat. The planet radiates significantly more heat into space than it receives from the distant sun, a clear sign that it has a potent internal energy source. This heat is not a product of nuclear fusion, as it would be in a star, but is primarily a remnant from its initial formation 4.5 billion years ago. The gravitational collapse of the primordial gas and dust that formed Jupiter generated an enormous amount of heat, and the planet is still slowly cooling down, releasing this ancient energy from its deep interior. This internal heat flux is a key driver of the planet's dynamic weather, fueling the powerful convection currents that create the belts, zones, and colossal storms we observe at the cloud tops. And among these storms, one reigns supreme, a feature so iconic it has become synonymous with Jupiter itself: the Great Red Spot. This is not a mere storm. It is a meteorological titan, an anticyclonic vortex of such staggering proportions that its existence has been documented for centuries. We know it has been continuously observed since at least 1830, and there are historical accounts of a permanent spot on Jupiter that likely refer to it, suggesting it has been raging for well over 300 years. Its size alone is a testament to its power. For most of its recorded history, the Great Red Spot has been vast enough to swallow the entire planet Earth whole, and at times could have accommodated 2 or even 3 Earths side by side. It is a storm on a truly planetary scale, a weather system larger than our entire world. Within this crimson vortex, the winds are a maelstrom of unimaginable fury. While the storm itself drifts slowly across the Jovian cloudscape, the winds circulating around its perimeter have been clocked at speeds up to 680 kilometers per hour, or about 425 miles per hour. These velocities are far in excess of the most powerful Category 5 hurricanes on Earth, creating a perpetual tempest of unparalleled violence. And yet, this ancient and powerful feature is not immutable. Over the past century, astronomers have observed a startling trend. The Great Red Spot is shrinking. It has become noticeably smaller and more circular in recent decades, and the reasons for this decline are still a subject of intense scientific debate. This colossal storm is not just a surface feature. It is a deeply rooted phenomenon. Data from the Juno mission has revealed that the vortex extends far down into the planet's atmosphere, with its roots reaching at least 350 kilometers, or over 200 miles, below the cloud tops. This incredible depth helps to explain its longevity, as it is being powered by forces and energy sources deep within Jupiter's interior. But the Great Red Spot is not the only remarkable storm system on the planet. Juno's unique polar orbit has given us our first clear views of Jupiter's poles, and they are unlike anything seen before. In these regions, we find not a single polar vortex, but stunning, stable geometric arrangements of cyclones. At the North Pole, a central cyclone is surrounded by 8 smaller cyclones, forming a near-perfect octagon. In the south, a central cyclone is encircled by 5 others, creating a stable pentagon. These polygonal storm systems are a breathtaking and entirely unexpected discovery, a testament to the complex and beautiful fluid dynamics that govern this giant world. These incredible storm systems, driven by the planet's internal heat and rapid rotation, are just one manifestation of the immense energy contained within Jupiter. An even more powerful and far-reaching influence stems from its deep metallic hydrogen interior, its magnetic field. This is not just a magnetic field in the terrestrial sense. It is a force of nature on a solar system-wide scale. It is, by a significant margin, the strongest magnetic field of any planet, a magnetic behemoth that dwarfs all others. Its strength at the cloud tops is estimated to be anywhere from 14 to 54 times more powerful than the magnetic field we experience at the surface of the Earth. To stand on a hypothetical Jovian surface would be to exist in a magnetic environment of overwhelming intensity. This colossal field is born from the planet's unique internal structure. As we have seen, the rapid 10-hour rotation of Jupiter churns the vast ocean of liquid metallic hydrogen that makes up its interior. This motion of an electrically conductive fluid creates powerful electrical currents, which in turn generate the planet's magnetic field in a process known as a planetary dynamo. The sheer volume and velocity of this metallic hydrogen dynamo are what give the Jovian magnetic field its extraordinary strength. The influence of this field extends far beyond the physical boundaries of the planet, creating a vast, invisible structure known as the magnetosphere. This is the region of space around Jupiter where the planet's magnetic field, rather than the solar wind, dominates the behavior of charged particles. And the scale of this magnetosphere is simply staggering. If our eyes were capable of seeing magnetic fields, the magnetosphere of Jupiter would appear larger in our night sky than the full moon, despite being hundreds of millions of kilometers away. It is a structure of such immense proportions that it could easily contain the sun and its visible corona. This magnetic bubble is not spherical. It is distorted and elongated by the constant pressure of the solar wind. A stream of charged particles flowing outward from the sun. On the side facing the sun, the magnetosphere is compressed, but on the side facing away, it is drawn out into an immense magnetic tail. A magnetotail of almost unbelievable length. This tail extends for over 1 billion kilometers, or more than 600 million miles, through the solar system. It is so long that it stretches all the way to the orbit of Saturn, a testament to the sheer power of the Jovian dynamo. Like Earth, Jupiter's powerful magnetic field funnels charged particles from the solar wind and from its own volcanic moon, Io, toward its poles. As these high-energy particles slam into the upper atmosphere, they excite the atmospheric gases, causing them to glow. This process creates spectacular and permanent aurora, light shows that are far more intense and energetic than our own northern and southern lights. These Jovian aurorae, visible primarily in ultraviolet and X-ray light, are a constant, shimmering crown of energy encircling the planet's poles, a visible manifestation of the titanic magnetic forces at play. For a long time, it was believed that the grandeur of Jupiter was limited to the planet itself and its moons. The idea of a ring system, like the magnificent one adorning Saturn, was not seriously considered for Jupiter. The planet appeared, even through the best telescopes, as a simple, unadorned disk. This perception was shattered in 1979, a pivotal year in our exploration of the outer solar system. It was then that the Voyager 1 spacecraft, during its historic flyby of Jupiter, turned its cameras to look back toward the sun through the planet's shadow. In this specific backlit geometry, a faint, ethereal structure was revealed. Jupiter had rings. This discovery was a profound surprise to the scientific community. Unlike Saturn's bright, icy rings, Jupiter's are faint, tenuous, and composed primarily of small, dark particles of dust rather than large chunks of ice. They are so faint that they are all but invisible from Earth, except with the most powerful telescopes and under perfect conditions. The discovery of these rings immediately posed a new question. Where did they come from? The dust particles that make up the rings are so small that they are constantly being eroded by Jupiter's harsh radiation environment and the pressure of sunlight. This means the ring system cannot be a static, primordial feature. It must be actively and continuously replenished. The leading theory, now well supported by observations, is that the rings are sourced from material blasted off of Jupiter's small inner moons. Micrometeoroid impacts on these moons, such as Metis and Adrastea, kick up clouds of dust. This dust then escapes the weak gravity of the small moons and is captured into orbit around Jupiter, forming the delicate ring structure we see. This makes the Jovian rings a dynamic, ever-changing system, a cosmic dust fountain fed by the constant bombardment of its innermost satellites. Further observations by the Galileo spacecraft and the Hubble Space Telescope have revealed that this ring system is more complex than initially thought, consisting of 4 main parts. The innermost part is a thick, donut-shaped torus of particles known as the halo ring. This extends outward to the brightest and most distinct part of the system, simply called the main ring. Beyond this lie 2 much fainter and broader rings, known as the gossamer rings, named for their sheer, transparent appearance. These gossamer rings are themselves associated with 2 specific moons, Amalthea and Thebe, and are composed of the dust ejected from their surfaces. The entire structure is a subtle and beautiful testament to the complex interplay of gravity, radiation, and orbital dynamics that governs the Jovian system. This intricate and dynamic ring system, fed by the constant shedding of its innermost attendants, serves as a delicate prelude to the true jewels of the Jovian system, its vast and diverse family of moons. For centuries, Jupiter was known to have just a handful of satellites, but with the advent of more powerful telescopes and robotic space probes, that number has grown dramatically. As of our current understanding, Jupiter is the confirmed host of 95 officially recognized moons, a bustling and complex system that resembles a miniature solar system in its own right. This legion of satellites ranges from captured, irregularly shaped rocks just a few kilometers across to worlds larger than planets. The story of their discovery is a pivotal chapter in the history of science, beginning in the early 17th century with the work of the Italian astronomer Galileo Galilei. In the year 1610, Galileo pointed his newly constructed telescope toward Jupiter and observed something extraordinary. Alongside the planet, he saw 4 small points of light, which he initially took to be fixed stars. However, as he observed them night after night, he noticed that they were not fixed at all. They were moving. And they were moving in orbit around Jupiter. This was a revolutionary, world-shattering discovery. It provided the first direct, unambiguous evidence that celestial bodies could orbit something other than the Earth. This simple observation struck a powerful blow against the prevailing geocentric model of the universe, the Ptolemaic system, which had held sway for over 1,400 years. The discovery of these 4 largest moons, which came to be known as the Galilean moons in his honor, was a cornerstone of the Copernican revolution, helping to firmly establish that the Earth was not the center of all creation. The moons themselves, Io, Europa, Ganymede, and Callisto, are not mere points of light, but are complex and fascinating worlds, each a unique planetary body with its own distinct character and history. The largest of them, Ganymede, holds the title of the largest moon in the entire solar system. It is a world of truly planetary proportions, larger even than the planet Mercury. Were it orbiting the Sun on its own, it would undoubtedly be classified as a planet. Ganymede is a world of rock and ice, its surface a patchwork of dark, ancient, heavily cratered terrain, and younger, brighter, grooved terrain, suggesting a complex geological history. But perhaps its most remarkable feature lies hidden within. Data from the Galileo spacecraft revealed that Ganymede is the only moon in the solar system known to possess its own intrinsic magnetic field. This field is generated by a dynamo effect within its liquid iron core, much like Earth's, creating its own small magnetosphere that is embedded within Jupiter's much larger one. This makes Ganymede a truly unique object, a moon with the internal complexity and dynamism of a full-fledged planet. Next, in this remarkable quartet, is Io, a world that could not be more different from icy Ganymede. Io is, without question, the most volcanically active body in the solar system. Its surface is a psychedelic canvas of yellow, red, orange, black, and white, all painted by the constant eruption of sulfur and its compounds. It is a world in perpetual geological torment, home to over 400 active volcanoes that spew plumes of gas and molten rock hundreds of kilometers into its thin atmosphere and out into space. This relentless volcanism is not driven by internal heat left over from its formation, but by a process known as tidal heating. As Io orbits Jupiter, the immense gravity of the giant planet, along with the regular gravitational tugs from its neighboring moons Europa and Ganymede, constantly flexes and kneads Io's interior. This constant friction generates an enormous amount of heat, keeping its subsurface rock molten and fueling its spectacular, planet-wide volcanic activity. Then there is Europa, a world that many scientists believe holds the greatest promise for finding extraterrestrial life in our solar system. At first glance, Europa appears as a bright, smooth, white sphere, crisscrossed by a complex web of dark lines and ridges. This smooth exterior is a shell of water ice, and the features on its surface strongly suggest that it is floating on a vast, liquid water ocean that lies beneath. The evidence for this subsurface ocean is compelling, from the analysis of the surface fractures, which resemble sea ice on Earth, to the detection of a weak magnetic field induced by Jupiter's, which is best explained by the presence of a global, salty, electrically conductive ocean. This hidden ocean, warmed by the same tidal heating that drives Ios, volcanoes, could contain more than twice the amount of water found in all of Earth's oceans combined. Shielded from radiation by the thick ice shell, this dark, vast, and potentially warm liquid water environment makes Europa a prime candidate in the search for life beyond our own world. The final member of the Galilean court is Callisto, a world that stands in stark contrast to its dynamic siblings. Its surface is the most heavily cratered of any object in the solar system, a testament to a long and quiet history. The sheer density of impact craters indicates that its surface is ancient and has not been renewed by geological activity for billions of years. Callisto is a geologically dead world, a frozen, battered relic from the early days of the solar system. Beyond these four giants, Jupiter's gravitational reach has captured a vast swarm of smaller bodies. Many of Jupiter's outer, smaller moons travel in irregular, highly inclined, and often retrograde orbits, moving in the opposite direction to the planet's spin. This is a telltale sign that they are not native to the Jovian system. The prevailing theory is that these are captured asteroids and comet fragments, stray wanderers that were gravitationally snared by the giant planet as it swept through the early solar system. They are the adopted children of Jupiter, a diverse collection of celestial flotsam that adds to the complexity and richness of this incredible planetary system. The profound influence and striking appearance of Jupiter have not been lost on humanity. Its presence has been known and chronicled since the earliest days of recorded history. Long before the invention of the telescope, ancient civilizations gazed upon the night sky and recognized 5 wandering stars, points of light that moved against the backdrop of the fixed constellations. These were the planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Among them, Jupiter shines with a particular brilliance. It is the 4th brightest object in our sky, outshone only by the Sun, the Moon, and the dazzling planet Venus. Its steady, silvery light made it a prominent and revered object for countless cultures across the globe. The planet we now call Jupiter was bestowed its name by the ancient Romans, who saw in its majestic, stately movement across the heavens a celestial embodiment of their supreme deity, the King of the gods. This association with power and royalty was a common thread. The ancient Greeks, from whom the Romans heavily borrowed their mythology, knew the planet as Phaethon, a name meaning blazing star, a fitting descriptor for its luminous appearance. Going back even further, the meticulous astronomers of ancient Babylonia, who kept detailed records of celestial movements on clay tablets, referred to the planet as Marduk, the patron deity of their great city of Babylon. For millennia, our understanding of Jupiter was limited to these naked eye observations, a bright, wandering point of light whose true nature remained a complete mystery. All of that changed in the early 17th century, with the advent of the telescope and the revolutionary work of Galileo Galilei. As we have seen, his discovery of the 4 largest moons in 1610 was a pivotal moment that reshaped our view of the cosmos. But his telescope revealed more than just the moons. For the first time, Jupiter was resolved from a point of light into a discernible disk, a true world. Galileo was able to observe the planet's flattened, oblate shape and see the faint, parallel bands of its atmosphere. These were the first telescopic observations of Jupiter, the dawn of a new era in planetary science, where our understanding would be built not just on observation of movement, but on the study of physical characteristics. Following Galileo, other astronomers turned their increasingly powerful telescopes toward the giant planet, slowly teasing out more of its secrets. In the year 1665, the Italian astronomer Giovanni Cassini, a meticulous observer, noted a persistent, oval-shaped feature in Jupiter's southern hemisphere. This permanent spot, as he called it, was the first recorded observation of what we now know as the Great Red Spot. This discovery marked the beginning of our long fascination with this colossal storm, a feature that has been studied and monitored for over 3.5 centuries. For the next 300 years, our knowledge of Jupiter grew incrementally, limited by the capabilities of ground-based telescopes. We learned about its rapid rotation, charted the movements of its cloud bands, and refined our estimates of its size and mass. But the true revolution in our understanding would have to wait for the dawn of the space age. The era of robotic exploration began in the 1970s, and Jupiter was a prime target. The first emissaries from Earth to visit this distant realm were the twin Pioneer spacecraft. Pioneer 10 made its historic flyby of Jupiter in 1973, followed by Pioneer 11 a year later. These were audacious, trailblazing missions. They were the first spacecraft to travel through the asteroid belt, the first to make close-up observations of Jupiter, and the first to use a planet's gravity to be flung onward to the outer solar system. They sent back the first ever close-up images of the planet and its great red spot, revealing a level of detail previously unimaginable. They also made the crucial discovery of Jupiter's intense radiation belts, a hazardous environment of high-energy particles trapped by its powerful magnetic field, a discovery that would be vital for the design of all future missions. The Pioneer missions were the reconnaissance, the first scouting of this new frontier. They were followed in 1979 by the twin Voyager spacecraft, Voyager 1 and Voyager 2. These were far more advanced probes, equipped with a sophisticated suite of instruments and high-resolution cameras. The Voyager flybys of Jupiter were a watershed moment, a quantum leap in our understanding of the Jovian system. they returned a treasure trove of breathtaking, detailed images of Jupiter's turbulent atmosphere, its rings, and its moons. It was Voyager 1 that discovered the faint ring system and the active volcanism on Io. The Voyagers revealed the complex, fractured surface of Europa and the ancient cratered face of Callisto. The data they collected essentially wrote the first modern textbook on the Jovian system, transforming it from a distant astronomical object into a complex and dynamic family of worlds. The flybys, however, were fleeting encounters, providing only a brief snapshot in time. To truly understand the long-term behavior of Jupiter and its moons, a dedicated, long-term presence was needed. This next great leap came with the Galileo spacecraft, named in honor of the astronomer who started it all. Launched in 1989, Galileo became the first spacecraft to enter into orbit around Jupiter, beginning its long and fruitful mission in 1995. For the next 8 years, Galileo was our permanent eye on the Jovian system, circling the planet dozens of times, making repeated close encounters with its large moons, and dropping a probe into Jupiter's atmosphere to take the first direct measurements of its composition and structure. The Galileo mission gave us a much deeper, more nuanced understanding of the system's intricate dynamics, revealing the secrets of Ganymede's magnetic field, strengthening the case for Europa's subsurface ocean, and providing a wealth of data on the planet's atmosphere and magnetosphere. The Galileo mission's long and incredibly productive vigil at Jupiter finally came to a dramatic and deliberate end in 2003. As the spacecraft's fuel ran critically low, mission planners at NASA faced a crucial decision. They could not risk leaving a derelict and uncontrollable spacecraft in orbit around Jupiter, where it might one day, perhaps thousands of years in the future, crash into one of the moons, particularly the potentially life-bearing Europa. The risk of contaminating Europa's pristine subsurface ocean with hardy terrestrial microbes that may have survived the journey on the spacecraft was a serious concern, a matter of profound ethical and scientific importance under the principles of planetary protection. To eliminate this risk entirely, a final sacrificial act was planned. The spacecraft was commanded to alter its course one last time, steering it directly toward the giant planet itself. In September of 2003, the Galileo spacecraft plunged into Jupiter's dense atmosphere, burning up and disintegrating, its constituent atoms becoming a part of the very world it had studied for so long. This intentional and responsible end to the mission paved the way for the next generation of explorers, chief among them being NASA's Juno spacecraft. Launched in 2011, Juno was designed with a very specific set of objectives, aiming to answer fundamental questions about Jupiter's origin, interior structure, and the workings of its powerful magnetic field. It entered into a unique, highly elliptical polar orbit around Jupiter in 2016, a trajectory that allows it to fly closer to the planet's cloud tops than any previous mission. This daring orbit takes it high above the poles, providing unprecedented views of these previously unexplored regions, before it dives down to skim just a few thousand kilometers above the atmosphere, passing beneath the most intense and hazardous parts of the radiation belts. This innovative orbital strategy has allowed Juno to peer deep into Jupiter's interior with its specialized suite of instruments, mapping its gravity and magnetic fields with exquisite precision. It is from this mission that we have learned about the fuzzy, dilute nature of Jupiter's core, the incredible depth of the Great Red Spot and the atmospheric jet streams, and the stunning polygonal arrangements of cyclones at the poles. The Juno mission is continuing to rewrite our understanding of how giant planets work, revealing a world that is even more complex, dynamic, and beautiful than we had ever imagined. The exploration of this magnificent system is an ongoing international endeavor. Hot on the heels of Juno, the European Space Agency's JUICE mission, which stands for Jupiter Icy Moons Explorer, is currently on its long journey to the outer solar system. Launched in 2023, JUICE is destined to perform a detailed investigation of Jupiter's 3 large ocean-bearing moons, Ganymede, Callisto, and Europa. Its primary goal is to characterize these moons as planetary objects and potential habitats, culminating in a historic maneuver where it will become the first spacecraft to enter into orbit around a moon other than our own, when it begins its dedicated orbital tour of Ganymede. Complementing this effort is NASA's Europa Clipper mission, also en route to the Jovian system. This spacecraft is specifically designed to investigate the habitability of Europa. Rather than entering into orbit around the icy moon, which would expose it to the full, damaging intensity of Jupiter's radiation belts, Europa Clipper will perform dozens of close flybys, dipping in for quick, targeted observations before retreating to the relative safety of a wider orbit around Jupiter. This strategy will allow it to gather crucial data on the thickness of Europa's ice shell, the depth and salinity of its subsurface ocean, and its complex chemistry, all while preserving the longevity of the spacecraft's sensitive electronics. These 2 missions, working in concert, represent the next great wave of exploration, promising to unlock the secrets of these mysterious water worlds. This intense focus on Jupiter and its moons is driven not just by scientific curiosity, but also by the profound role the planet plays in our solar system. Jupiter is often referred to as the vacuum cleaner of the solar system, a title it has earned through its immense gravitational influence. Its sheer mass acts as a giant cosmic shield for the inner planets, including Earth. It attracts and absorbs a significant number of inbound comets and asteroids, sweeping its orbital neighborhood clear of potentially hazardous impactors. Without Jupiter's protective presence, the rate of asteroid and comet impacts on Earth would likely be much higher, a factor that could have had profound consequences for the evolution of life on our planet. The evidence for this protective role is stark. It is estimated that Jupiter gets hit by asteroids and comets about 200 times more often than Earth does. We were given a dramatic, real-time demonstration of this process in 1994, in an event that captivated astronomers and the public around the world. A comet, named Shoemaker-Levy 9 after its discoverers, had been captured into orbit around Jupiter and was torn apart by the planet's intense tidal forces. The resulting train of more than 20 cometary fragments then proceeded to slam into Jupiter's southern hemisphere, one by one, over the course of several days. This was the first time in human history that we had witnessed a direct collision between two solar system bodies. The impacts created enormous dark scars in Jupiter's atmosphere, some of them larger than the Earth, providing a spectacular and sobering display of the immense energies involved in such cosmic collisions. The event served as a powerful reminder of Jupiter's role as a gravitational gatekeeper and the dynamic and sometimes violent nature of our solar system. Beyond its role as a celestial guardian, Jupiter is also a source of powerful, naturally generated radio waves. These radio emissions, produced by energetic electrons spiraling within its immense magnetic field, are so strong that at certain frequencies, they can sometimes outshine the radio emissions from our own sun as received by Earth. This makes Jupiter a major and fascinating source of celestial radio noise, one that has been studied by radio astronomers since its discovery in the 1950s. This giant planet is not just a passive object in space. It is an active, broadcasting entity, a testament to the powerful physical processes that govern its existence. These processes have been at work for a very long time, as Jupiter is believed to be the oldest planet in our solar system. Formed just a few million years after the Sun itself, about 4.6 billion years ago, Jupiter's rapid growth had a profound and lasting impact on the architecture of the entire system. Its enormous gravity has sculpted the orbits of the other planets, influenced the distribution of asteroids in the asteroid belt, and dictated the delivery of water and other volatile materials to the inner solar system. Understanding Jupiter is not just about understanding one planet. It is about understanding the origin and evolution of our entire cosmic neighborhood. The shaping of our solar system by Jupiter's immense gravitational influence is a story of dynamic and sometimes chaotic celestial mechanics, a history that scientists are still working to piece together. One of the most compelling and dramatic theories to emerge in recent years is known as the Grand Tack hypothesis. This model suggests that Jupiter's early life was not a quiet, stable affair. Instead, It proposes that soon after its formation in the outer solar system, the giant planet began to migrate inward, its orbit spiraling closer and closer to the Sun. This inward journey, driven by interactions with the dense disk of gas and dust that still filled the young solar system, would have had catastrophic consequences for the inner regions. As Jupiter tacked inward like a sailboat changing direction, its gravity would have scattered the primordial planetesimals, the small rocky bodies that were in the process of forming the terrestrial planets. This gravitational disruption is thought to be responsible for the relatively small size of Mars, which was essentially starved of building materials by Jupiter's passage. The hypothesis continues that after migrating inward to roughly the current orbit of Mars, Jupiter was captured in a gravitational resonance with the newly forming Saturn, which was also migrating inward behind it. This interaction halted Jupiter's inward march and reversed its course, causing both giant planets to migrate back outward toward their current stable orbits. This grand celestial dance, a planetary migration on a massive scale, would have fundamentally reshaped the distribution of material in the early solar system, explaining many of the architectural features we observe today, from the composition of the asteroid belt to the orbits of the inner planets. This model, while still a hypothesis, highlights the central role Jupiter played as the primary architect of our planetary family. In the wider cosmic context, Jupiter serves as a crucial benchmark, a local example of a common class of planets found orbiting other stars. The thousands of exoplanets discovered in recent decades have revealed that giant planets are a common outcome of planet formation. A significant number of these are so-called hot Jupiters, gas giants that orbit extremely close to their parent stars, with orbital periods of just a few days. The existence of these hot Jupiters was a major surprise and strongly supports the idea that planetary migration, like that proposed in the Grand Tack hypothesis, is a common and important process in the formation of planetary systems. By studying our own Jupiter in detail, we gain invaluable insights into the nature of these distant worlds, which we can often only observe as faint, shadowy transits across their stars. Jupiter is our archetype, the template against which we measure and attempt to understand the myriad of giant planets scattered throughout the galaxy. The very language we use to describe this giant world reflects its historical and scientific importance. The adjectival form for Jupiter is Jovian, a term derived directly from Iovis, the genitive case of the Latin name for the Roman god king. Thus, we speak of the Jovian system, the Jovian atmosphere, and the Jovian magnetosphere. For terms requiring a more classical scientific root, astronomers sometimes turn to the Greek equivalent, using the prefix xeno, derived from Zeus, the Greek counterpart to the Roman Jupiter. So, for example, the study of Jupiter's geology might be termed xenology, and its cartography xenography, though these terms are more specialized and less common than the ubiquitous Jovian. For amateur and professional astronomers alike, the Jovian system provides a constant source of observational wonder. One of the most accessible and rewarding sights is the transit of Jupiter's Galilean moons. With a moderately sized telescope, one can watch these small worlds pass in front of the planet, casting their tiny, perfectly black, circular shadows onto the swirling cloud tops below. Observing these shadow transits is to witness a miniature eclipse, a direct and visible demonstration of the three-dimensional nature of the solar system, an experience that connects the modern observer directly to the foundational discoveries of Galileo Galilei 4 centuries ago. While the planet itself is a dynamic and fascinating object of study, the question of life in the Jovian system has shifted its focus away from the turbulent, crushing atmosphere of Jupiter itself. The conditions on the gas giant, the lack of a solid surface, the extreme pressures and temperatures, and the violent planet-wide storms make the existence of life as we know it there highly unlikely. Instead, the scientific search for extraterrestrial life has turned its attention to Jupiter's moons, particularly the ocean world of Europa, and to a lesser extent, Ganymede and Callisto. These icy satellites, with their potential for vast, hidden oceans of liquid water, represent some of the most compelling and promising locations to search for life beyond Earth. Jupiter, therefore, has evolved in our perception from a single object of study to the host of a system of potentially habitable worlds. As we have noted, Jupiter shares the same basic ingredients as a star. It is composed almost entirely of hydrogen and helium. The fundamental difference between a large gas giant and a small star is one of mass. A celestial body must reach a critical mass, estimated to be about 70 to 80 times the current mass of Jupiter, for the pressure and temperature in its core to become high enough to ignite sustained nuclear fusion of hydrogen into helium. Jupiter, for all its immense size, falls well short of this threshold. It is a star that never was, a colossal ball of gas that collected the majority of the leftover material after the sun formed, but never quite grew large enough to set itself alight. This distinction defines its nature as a planet, albeit one that straddles the boundary of what is possible for a world. The sheer distance of Jupiter from the Sun governs the timeline of our communications and observations. Sunlight, which takes just over 8 minutes to reach Earth, embarks on a much longer journey to reach the king of planets. It takes approximately 43 minutes for the light and heat from our star to travel across the vast expanse of the inner solar system and reach the cloud tops of Jupiter. This light travel time is a constant reminder of the immense scales we are dealing with when we explore the outer solar system. A command sent from Earth to the Juno spacecraft takes 43 minutes to arrive, and the data it sends back takes another 43 minutes to return. A cosmic time lag that engineers and scientists must always factor into their plans. Once at Jupiter, one would experience a profound increase in the force of gravity. The planet's immense mass and size combine to produce a surface gravity that is 2.5 times that of Earth. A person weighing 80 kilograms, or about 176 pounds, on Earth would feel as if they weighed 200 kilograms, or 440 pounds, at the cloud tops of Jupiter. This powerful gravitational pull is what allows Jupiter to retain its vast, deep atmosphere of light gases like hydrogen and helium, which a smaller world like Earth could not hold on to. Yet, despite being closer to the planet's hot interior, the temperature at the top of these clouds is frigid. The average temperature in the upper atmosphere, where the pressure is similar to that at Earth's surface, is about minus 110 degrees Celsius, which is equivalent to minus 166 degrees Fahrenheit. This is because the cloud tops are very far from the planet's internal heat source and receive only weak sunlight, creating a cold, inhospitable environment at the visible boundary of this giant world. The planet's incredible rotational velocity, that dizzying sub-10-hour day, is not just a curiosity that flattens its poles and creates a fleeting cycle of day and night. It is a fundamental engine driving some of Jupiter's most powerful and defining characteristics. As we've explored, this rapid spin is the crucial ingredient that, when combined with the vast, electrically conductive ocean of metallic hydrogen in its interior, generates the planet's colossal magnetic field. The dynamo theory, which explains the origin of planetary magnetic fields, requires two key components: a conductive fluid and rapid rotation. Jupiter possesses both of these in extreme abundance. The faster a planet spins, the more organized and powerful the convective currents within its fluid core become, leading to a more efficient and stronger dynamo. Jupiter's swift rotation supercharges this process, creating a magnetic field of unrivaled strength and a magnetosphere of unparalleled scale. This vast and complex system, encompassing the planet, its powerful magnetic field, its swarms of moons, and its delicate rings, is often described by astronomers not just as a planetary system, but as a mini-solar system. This is not mere hyperbole. The Jovian system is a remarkably complete and self-contained celestial neighborhood. It has a central, dominant body in Jupiter, analogous to the Sun. It has its own retinue of worlds, the moons, orbiting in a relatively flat plane, much like the planets of our solar system. The Galilean moons, in particular, exhibit a fascinating orbital harmony and display a diversity of characteristics that rivals that of the terrestrial planets. From the fiery volcanism of Io to the hidden oceans of Europa, the Jovian system is a microcosm of the larger solar system, a natural laboratory for studying the processes of planet and moon formation on a more manageable scale. Within this miniature solar system, the distribution of mass is incredibly lopsided. The 4 Galilean moons, despite being just 4 out of 95, are so overwhelmingly dominant that they account for a staggering 99.997% of the total mass orbiting Jupiter. The other 91 moons and the entire ring system combined make up just a tiny, almost negligible fraction of the system's total mass. This stark imbalance is a testament to the conditions in the early Jovian system, where these 4 moons likely formed from a circumplanetary disk of gas and dust, growing to planetary size, while the smaller outer moons were captured later from chaotic orbits. The structure of Jupiter's atmosphere also invites comparison with our own world, though the differences are as striking as the similarities. While Earth's atmosphere is commonly divided into 5 distinct layers, the troposphere, stratosphere, mesosphere, thermosphere, and exosphere, Jupiter's is typically modeled with just 4. It possesses a troposphere, where its weather occurs, a stratosphere, a thermosphere, and an exosphere. It notably lacks a mesosphere, the layer that on Earth is responsible for burning up most meteors. The reasons for this structural difference lie in the vastly different chemistry and temperature profiles of the 2 atmospheres, a reflection of Jupiter's unique composition and its greater distance from the Sun. For any hypothetical spacecraft or probe, navigating this colossal atmosphere would be an impossible challenge. The pressure inside Jupiter increases at an astonishing rate with depth. Any vehicle attempting to fly through it, even one built to withstand extreme conditions, would be inexorably crushed by the immense weight of the overlying gas. The Galileo probe, which was specifically designed for its one-way journey into the clouds, survived for only about an hour, transmitting data until it reached a depth where the pressure was about 22 times that of Earth's sea level. It was destroyed by the combination of rising pressure and temperature long before it could penetrate any significant distance into the planet's vast, gaseous ocean. The vibrant and dramatic colors that make Jupiter such a visually stunning object are the result of subtle chemical processes occurring high in its atmosphere. The base color of the clouds is largely white due to the presence of frozen ammonia crystals. The rich palette of reds, oranges, yellows, and browns is thought to be created by the presence of chromophores, or color-bearing compounds. These are believed to be plumes of sulfur and phosphorus containing gases that are dredged up from deeper, warmer layers of the atmosphere by powerful convective currents. When these gases reach the upper atmosphere, they are exposed to the sun's ultraviolet radiation, which triggers chemical reactions that transform them into the colorful, complex compounds that paint the Jovian cloudscape. The exploration of this complex world has been a multi-generational effort, a long and patient campaign of robotic emissaries. The early flyby missions, Pioneer, Voyager, and later the Ulysses solar probe, the Cassini mission on its way to Saturn, and the New Horizons mission on its way to Pluto, each provided valuable, fleeting snapshots of the Jovian system, each building on the knowledge of the last. They were the scouts and trailblazers, charting the territory and revealing the tantalizing questions that would require a more dedicated presence to answer. This led to the era of orbiters, with the Galileo mission providing the first long-term study, and the current Juno mission offering an unprecedentedly detailed and focused investigation. The Juno mission's unique polar orbit has been particularly revolutionary. By flying over the poles, it has given us our first clear views of these regions, revealing the stunning, geometrically arranged cyclones. This vantage point has also allowed scientists to probe the fundamental differences between the two main types of storms on Jupiter: cyclones and anticyclones. Cyclones, like the polar formations, rotate in the same direction as the planets spin and have been found to be warmer at their tops and colder at their bottoms. Anticyclones, like the Great Red Spot, rotate in the opposite direction and exhibit the reverse temperature structure, being colder at the top and warmer at the bottom. This thermal data provides crucial clues about the vertical structure and energy flow within these colossal weather systems. Juno's gravity measurements have also allowed us to probe the depth of the planet's most prominent features: the powerful jet streams that create the colored bands of the belts and zones. The data reveals that these east-west winds are not just a thin, surface-level phenomenon. They are incredibly deep, extending down into the atmosphere to a depth of about 3,200 kilometers, or roughly 2,000 miles. This is a staggering depth, indicating that the jet streams are a fundamental feature of the planet's dynamics, driven by processes deep within its interior, rather than by solar heating at the cloud tops. The sheer volume and momentum of these deep-seated atmospheric flows are what make them so stable and powerful, shaping the entire visible face of the planet. The deep-seated nature of these powerful jet streams appears to be intimately linked to one of the most puzzling and long-standing mysteries of Jupiter's atmosphere: the distribution of ammonia gas. Data from the Juno mission's microwave radiometer, an instrument capable of peering deep beneath the visible cloud tops, has revealed a fascinating connection. The concentration of ammonia in the atmosphere is not uniform. Instead, it seems to vary in a way that is directly correlated with the banded structure of the belts and zones. In particular, there is a prominent belt of ammonia-rich gas circling the planet's equator, a feature that seems to be associated with the powerful equatorial jet stream. This suggests that the same deep atmospheric circulation that drives the winds is also responsible for transporting and concentrating chemical compounds, creating a kind of atmospheric weather that extends far below the surface we see. Unraveling this connection is key to understanding the full three-dimensional structure of Jupiter's colossal weather engine. While this deep atmosphere is a realm of complex chemistry and dynamics, the space surrounding Jupiter is dominated by the invisible but powerful forces of its magnetic field. This field, as we have seen, is the most formidable in the solar system, and its influence creates an environment of extreme radiation. The magnetosphere traps vast quantities of high-energy charged particles, primarily electrons and ions, accelerating them to nearly the speed of light. These particles are concentrated into intense radiation belts, similar in nature to Earth's Van Allen belts, but thousands of times more powerful. These radiation belts pose a severe and constant threat to any spacecraft operating in the Jovian system. The high-energy particles can penetrate shielding and wreak havoc on sensitive electronics, causing malfunctions and permanent damage. This is why the orbits of long-term missions like Galileo and Juno have to be carefully designed to minimize their time within the most intense regions of these belts, a constant challenge for mission planners navigating this hazardous environment. This powerful magnetic field, which creates such a dangerous radiation environment, is also responsible for shaping the planet's faint and delicate ring system. The small, dark dust particles that make up the rings are not only governed by gravity, but are also influenced by electromagnetic forces. Because the particles are electrically charged, their paths are perturbed by the planet's rotating magnetic field, a phenomenon that helps to explain the structure of the broad, puffy halo ring that lies closest to the planet. The rings themselves, being so faint and tenuous, are almost impossible to see from Earth under normal conditions. Their discovery by Voyager 1 required a specific and advantageous viewing geometry, looking back through the system so that the tiny particles would be illuminated by the sun from behind. This technique, called forward scattering, dramatically enhances the visibility of small dust particles, making the otherwise invisible rings stand out against the darkness of space. It is only in this backlit configuration that the full ethereal beauty of Jupiter's subtle rings can be truly appreciated. Just as the rings are a subtle feature of the central system, the Trojan asteroids that share Jupiter's orbit are a quiet but significant presence. These thousands of captured bodies clustered in the stable, Lagrange points ahead of and behind the planet, are a diverse population of cosmic fossils from the early solar system. The largest among them is a significant body in its own right, an asteroid named 624 Hector. It is a large, elongated object, and observations suggest it might even be a binary asteroid, two separate bodies in close contact or orbiting each other. A complex world let masquerading as a single asteroid. The study of these Trojan asteroids, which are the target of NASA's Lucy mission, promises to reveal crucial information about the composition and conditions of the primordial solar system. The intricate four-part structure of the ring system, the halo, the main ring, and the two even fainter gossamer rings, is, as we've noted, directly tied to the planet's innermost moons. The two gossamer rings, in particular, are named after the moons from which their material is believed to originate. The Amalthea gossamer ring, and the Thebe gossamer ring. These rings are exceptionally faint and diffuse, their particles slowly spiraling away from their parent moons under the influence of various forces, creating a vast, tenuous disk of dust that extends far out into the Jovian system. This delicate, dusty environment stands in stark contrast to the solid, ancient nature of some of Jupiter's larger moons, like Callisto. Its heavily cratered surface, as we've explored, is a sign of its geological inactivity. It lacks any significant internal heat source to drive volcanism or tectonic activity, and thus its surface has simply been preserving the scars of impacts for billions of years, a frozen record of the history of bombardment in the outer solar system. This quiet, ancient world is the antithesis of its sibling, Io. The vibrant, almost garish colors of Io are a direct product of its rampant volcanism. The constant eruptions spew out a variety of sulfur compounds, which then condense and frost the surface in shades of yellow, red, orange, and white. This volcanic material not only paints Io's surface, but is also the primary source of the plasma that fills Jupiter's enormous magnetosphere. As the ejected particles are stripped away and ionized, feeding the very radiation belts that make the system so hazardous. Deep within the heart of this entire system, at the very center of Jupiter, the conditions reach a level of extremity that challenges our understanding of matter. The immense pressure and gravitational compression generate incredible heat, with theoretical models suggesting that the temperature at Jupiter's core could reach as high as 50,000 degrees Celsius, which is about 90,000 degrees Fahrenheit. This is a temperature hotter than the surface of the sun, a blistering heat that is a remnant of the planet's violent formation and slow, ongoing contraction. It is this immense internal engine that ultimately drives the planet's complex weather and powerful magnetic field. From its fiery core to its outermost moons, Jupiter's story is the story of the formation of our solar system. In the great cloud of gas and dust from which the sun was born, Jupiter was the first planet to form. It rapidly swept up the majority of the leftover mass, growing into the giant it is today. This process of accretion and growth profoundly shaped the subsequent formation of the other planets, dictating how much material was available and where it could accumulate. Jupiter is not just a planet in the solar system. It is the planet that made the solar system what it is today, the ancient king that has reigned since the very beginning. And so, our long journey to the king of planets comes to a close. We have traveled from the swirling, crimson fury of its colossal storms, down through the gossamer veil of its clouds, into an ocean of liquid metal, where the laws of physics are forged anew. We have explored the intricate dance of its 95 moons, from the volcanic torment of Io to the profound, silent promise of a hidden ocean on Europa. We have seen how this single, immense world has served as both the architect and the guardian of our solar system. Its gravitational embrace shaping the very ground beneath our feet billions of years ago. The story of Jupiter is a testament to the grand, dynamic, and often violent nature of the cosmos. It is a world that is both a failed star and a perfect planet, a place of unimaginable extremes that continues to challenge our understanding with every new piece of data sent back across the void. Though our narrative ends here, the exploration does not. New emissaries are already on their way, continuing our relentless quest for knowledge, seeking answers to questions about the origins of our solar system and the potential for life beyond our world. The next time you gaze up into the clear, dark canvas of the night sky and find that bright, unwavering point of light, you will see it differently. You will see not just a wandering star, but a system of worlds. You will see the deep, driving heat of its core, the ancient, spinning storms, the faint, dusty rings, and the glimmer of its attendant moons. You will see a history 4.5 billion years long, and a future of discovery that is still waiting to be written. You will see Jupiter not as a distant object, but as a fundamental part of our own cosmic story, a single point of light in our sky, now transformed into a universe of wonders.